Hello everyone, we're approaching, not quite exactly there, but approaching the end of our study of the periodic table. Still a little bit left to do after this, but here we're going to talk a little bit about energy involved in chemical reactions, and near the end we'll define what equilibrium is. And as you see there, just 9 total slides. This is mostly definition and should be pretty straightforward. Are we ready? Let's go. A couple of definitions here: oxidation and reduction. Oxidation is a reaction that involves oxygen, and you'll see what I mean in just a moment here. But oxidation, you ever get some of that white gunk maybe on the outside of a metal container and have to clean that off? We call that oxidation. That's a reaction of the metal with the oxygen in the moisture in the air. What happens here is that the metal will lose some of the electrons, and that's common sense because that's something we've talked about a lot already. And the oxygen will be the nonmetal that will gain those electrons. For example, look at mercury oxide. Okay, reminder about the 2's right here. Remember, these 2's make us balance the equation. Okay, let me clean that off. Okay, remember, mercury with 2 valence electrons to give away, oxygen with 6 valence electrons and needs 2 more. But you have to remember, oxygen is diatomic. That's why we have to put 2 oxygens here. So these 2 electrons can go right on in here, right on in here. Now oxygen has 8 and oxygen's very happy. But what about this other one here? Where will this oxygen get its other 2 electrons? Well, remember, this is why we have to balance. So we need a second mercury to give those electrons to the oxygen. And we end up forming 2 mercury oxide molecules. That's where this other 2 comes into play. So 1 here and 1 here. And remember, this is the reason we have to balance. And you can see with the electron dot notation why we need that second mercury, because remember, oxygen is diatomic. Each mercury, as you just saw, gives 2 electrons to an oxygen atom. And this is called oxidation here. In oxidation, the metal, the mercury, in the example you just saw, lost those electrons and the oxygen gained those electrons. So that's called oxidation. In reduction, that's the oxygen gaining the electrons. So the mercury, the metal, has been oxidized. The oxygen, as you see here, is getting reduced. The gaining of electrons. In that above example and the dot notation you just saw, the oxygen's ability to add even more electrons is now reduced, and that's because each of those 2 oxygen atoms now has 8 valence electrons. Therefore, those atoms don't want to gain any more. So they reduced their ability to add more electrons once they reach their 8 that they want in the valence level. The metal is oxidized, the nonmetal oxygen is reduced. So oxidation is when the metal, in that case mercury, gives away the electrons, and the reduction is the oxygen adding those electrons and now cannot add any more. That ability has now been reduced. Metal's oxidized, nonmetal oxygen is reduced. Ready? In energy exchanges, in all chemical reactions, energy is exchanged, and the energy could change form from one kind of energy to another. The law of conservation of energy you will see on the screen before too long. But all chemical reactions have an exchange of energy. The added energy can help break the bonds, and then those particles can recombine, rebonding as you see on the screen there, and the atoms that rebond release that energy. And that's why a lot of them end up feeling hot, exothermic, as you'll see in just a moment. But there's always an exchange of energy in any chemical reaction. A couple more definitions. Endothermic. Endo sounds a little like enter, and thermic means heat. So an endothermic reaction is one that absorbs heat. Heat goes into the reaction. That's called endothermic, entering heat. And in that case, decompositions are going to require us to add heat, energy, in order to break those bonds. Remember the second line right here, added energy breaks the bonds. So endothermic reactions, most of the decompositions are endothermic because they require us adding heat energy in order to separate the molecules. Most of the other reactions are exothermic. They give off heat and they're going to feel warm to the touch. Endothermic is going to feel cool to the touch. Exothermic is the heat coming off the reaction, so we will feel that heat leaving the reaction and hitting our bodies. Exo, exit, and thermic, energy. Exothermic, giving off heat. Heat is leaving that reaction. Most of your combinations, your single replacements, and your double replacement reactions, those are exothermic. They're going to give off the heat because these atoms have rebonded, and that energy released we may feel as heat. So exothermic. Ready? As we said, most of this is definition type stuff. Now remember, we've had the law of conservation of matter before, which said matter cannot be created or destroyed, but can change from one form into another. There are other laws of conservation we'll see later as well, but the law of conservation of energy is very, very similar. In fact, all the laws of conservation are. Here's a law of conservation of energy. Energy cannot be created or destroyed, but can change form and location. So an energy will transfer from one location to another, but the total amount of energy will remain the same both before and after the reaction occurs. All reactions conserve energy. Again, the energy has changed form and position or location, but if we were to add up all the energy before and after the reaction, we get the same totals. For example, you burn some firewood. Okay, build a campfire, burn the wood. The energy that comes off the wood as heat radiates and eventually will dissipate into the atmosphere and just spread out so thin that we can't notice that heat anymore, especially when we get a distance away from that fire. But the energy still exists. The heat radiates off the wood into the atmosphere. Another example, plants will absorb light energy from the sun and turn that light energy into chemical energy. Remember, photosynthesis is the process that green plants use in order to make their own food. A chemical called chlorophyll will absorb that light energy, and the plant will turn that energy into the chemical energy or the food that the plant needs to survive, thrive, and reproduce. But no matter what the reactions are, the law of conservation of energy works. The total amount of energy will not change, just the kind of energy and where that energy is now located will. One more time, read that first line again. Energy cannot be created or destroyed, but can change form and location. That's a law of conservation of energy. Ready? Okay, reaction rates. Do you think all reactions occur at the same rate? Well, they don't. They react at different rates depending on the reaction and other conditions, but all reactions need three things in order to occur. So these three things are needed for a reaction to occur. First, the reactants particles must collide. Now let's remember the equation. In really general terms here, the reactants are the before on the left side of the equation, and the products are the after on the right side. So obviously, before and after. Okay, so we say the reactants particles must collide. We have the reactants here. Remember, there's always motion in the particles. When they collide, when they come together, then the reaction could take place. The second condition, when those particles collide, the particles must line up correctly. Excuse me. If the particles just kind of bounce off each other, they're not lined up just right, then a reaction may not occur. But if they hit each other at just the right angles and speeds, well, then a chemical change can take place. And step number 3, the particles need enough energy, especially in decompositions. If we don't supply enough energy, then we may not be able to break those bonds. So for reactions to occur, there must be enough energy. Number one, particles must collide. Number two, they have to collide just right, must align themselves correctly. And number three, they have to have enough energy in order for the reaction to occur. Another definition here, reaction rate. This is one of those duh definitions, how quickly the reactants become products. So that's fancy terms for how fast the reaction occurs. The reactants turn into the products, and that's the reaction rate, the speed at which this happens. And here are some factors that can affect the reaction rate. Heat, concentration, surface area, stirring, and some others. And if you see pages 162 to 163, you'll see a few more added to this list. If we heat up the reaction, well, we're supplying more energy. See number three again, particles must have enough energy. So that can cause the reaction to speed up and occur a little bit faster. Concentration means how many of the atoms or molecules are involved. So if we have more atoms and molecules, then we're more likely for some of them to undergo the reaction and get the desired products. Surface area, if we have a wider surface area, think of evaporation that we've talked about before. The bigger the surface area, the wider the top of the liquid, the more the molecules can jump off. So if we have a bigger surface area that will allow the reactants to collide with each other, the better chance we have at a faster reaction rate. When we stir, we're adding kinetic energy. So we're getting those particles on the reactant side to bang into each other much more and even faster, and that can cause a drastic change and increase in the rate. And there are other things you see on pages 162 and 163 that can help determine how fast a reaction occurs. But remember, these three things are needed. The reactants, particles must collide, they must collide just right, and they need enough energy, and that will affect their reaction rate. Ready? Are reactions reversible? Can we get what we started with if we turn the reaction around? In some cases, no. I mean, once you burn a candle, you burn that wick, the wick melts the wax, that wax spreads around on the bottom. Well, you can probably get the wax and build a candle, but where are you going to get the new material for the wick? That wick is gone. So we really can't reverse that particular reaction. And many reactions are irreversible. Sodium chloride is almost impossible, if not impossible, to separate into sodium and chlorine. However, some reactions are reversible. Let me quickly write the equation for water. Okay, you're familiar with this. Hydrogen is diatomic, so is oxygen. So we end up with two water molecules, assuming no mistakes there. Reversible means, let's turn this around. So that combination reaction is now becoming a decomposition reaction. Of course, I would write it left to right, in which the bond between hydrogen and oxygen are now separated, and that can be done with electricity. Here's another example. We talked about mercury and oxygen a few minutes ago. Mercury plus diatomic oxygen can give us 2 molecules of mercury oxide. This is reversible, so just imagine turning this around. I'll give you a moment to think about what we would end up with. Again, reversible, just turn this around. What would we get? Well, that mercury oxide will be separated back into the mercury atoms and the oxygen diatomic molecule. But remember, the 2's in front, the coefficients, will still balance the equation. So here's an example of a reversible reaction. The combination one got reversed and became a decomposition. Now, for that to happen, the products must remain contained. We don't want the oxygen to flow off into the atmosphere. We want to be able to contain them, and enough energy present to reverse the original reaction. So we have to keep the products contained and still have enough energy, especially if a combination is going to be split back up into a decomposition. That 2HGO right there, we have to have enough energy in order to separate that bond into the mercury and the oxygen. Ready? Okay, equilibrium, we're almost done here for today. In a balanced system, all influences cancel each other. That means no matter what's happening, something is going to cancel something else. Kind of like a tug of war. If the forces on both sides of the rope are pulling evenly but in opposite directions, that's called balance. The forces will cancel and nobody's going to move that rope. And until someone's stronger than the other one, that's going to be a tie. So in a balanced system, think of the reactions. If all the influences that we talked about already, had on the screen a moment ago, if they cancel each other out, then we have what's called equilibrium. The forces are all the same strength in opposite directions, just like I mentioned a moment ago with the tug of war. If the two teams are pulling with the same strength in complete opposite directions, that rope is not going anywhere. In a physical equilibrium, think of evaporation and condensation. Well, if I have water in a container and it's warm enough in the room, the water is going to evaporate. If it's an open container like a cup, the water's going into the air. But if we put a lid on the container and we're able to keep those water vapor molecules from escaping, well, we could have those molecules condense back into liquid form when enough of them get built up. So we need the evaporation and condensation, this is just an example, in a closed container, and that can happen at the same rate. So no matter which molecules ended up evaporating and then condensing, we get the total amount of liquid and gas after changes occur as when we started. That's called equilibrium, equal. In a chemical equilibrium, forward and reverse reactions, the combination and the decomposition reactions occur at the same rate. So the two parts of the water molecule, the hydrogen and the oxygen that come together to make the water, that decomposition to put the elements back into hydrogen and oxygen, if they occur at the same rate, we're going to have equilibrium, the same number of individual diatomic hydrogen and oxygen and water molecules at any point during this equilibrium process. So equilibrium is when all the forces cancel and we maintain what we started with equal to what we are at any given point. That's equilibrium. Ready? All right. How can we change equilibrium? Things are in equilibrium. Can we cause equilibrium to go away? Certain changes will break that equilibrium and we'll have more of something and less of something else, some other part. Concentration, if we are to add more of the reactants maybe, add more of the substances, well then obviously we have broken that equilibrium. We don't have the same as what we started with. So concentration, by adding or removing substances, will change the rate and break the equilibrium. If we add more heat, the reaction is more endothermic, putting more heat into the reaction, well then we could cause even more of the process of the reaction to occur. If we have less heat, then cool things down, well then less of the reaction is likely to occur. So less heat, remember that's exothermic as heat is leaving, that's going to change and break the equilibrium as well. So we're not going to have the same things we started with. Pressure, more gas particles. The denser that gas is, the closer those molecules are together, and the more of those we have, the more pressure. If we have fewer particles, we have less pressure, so the equilibrium again is broken. So if we have gases, we condense those closer together but keep them in gas form, the reaction rates are going to change. Equilibrium has been broken. Now, even if we do one of these three processes, if we stop adding concentration, changing the temperature, the pressure, eventually we'll get that equilibrium back. Now it depends on how big of a change in these three things that we did that would determine how long it would take to get back to equilibrium. But eventually those reactions will return to equilibrium. Ready? All right, that's going to do it for this set of notes. My super hilarious The End joke. Thank you, and we'll see you in Chapter 8.